So thinking back on the simulation, there was a way that we can analyze the motion by looking independently at the vertical velocity and the horizontal velocity at different times along the path. We're going to need some math to help us figure out what these values are, given the fact that most problems will measure a speed that is a combination of both the vertical and the horizontal velocities. So you might see something like this, where it says a rocket is launched at a speed of 12 meters per second at an angle of 65 degrees above the horizontal. Make sure your calculator is in degree mode for this, but this is going to have a setup that looks very similar to this drawing, where we have the initial velocity as 12 meters per second, and the angle is 65 degrees above the horizontal. We need to break this 12 meters per second into a horizontal component, a Vx, and a vertical component, a Vy. We can do that because this forms a right triangle, and we can use our SOHCAHTOA math in order to figure out, given the angle and the hypotenuse, find out the side length, which is the velocity in that direction. All right, so let's look at x first. We know that x is the adjacent side, so therefore I'm going to want to use cosine, and the cosine of the angle is the adjacent side, the Vx, all over the hypotenuse, or 12 meters per second in this case. I'm doing some math, algebra. I'm going to multiply both sides by 12. 12 times the cosine of 65. Make sure it's in degree mode. You get about 5.1. So that becomes the value of that horizontal velocity. We'll do the same thing in y, where we're going to use the component of our 12, but only the vertical component. So I'm going to use the opposite side. So I'll have sine as my trig function. The sine of the angle is equal to the opposite side over the hypotenuse. That becomes 12 times the sine of 65, and I end up with about 10.9 meters per second. My ideas and goals for you is to always look at what they give you as an initial velocity and be able to separate that into its components using your SOHCAHTOA. You can even add to your equation sheet the fact that Vx is always going to have a similar pattern. So if we look at our right triangle, and I'm going to just draw a really quick right triangle right here. If this is our initial velocity, Vx in the V initial in the x direction is always going to be equal to the initial velocity times the cosine, because that's the adjacent angle, and the Vy initial in the y direction is always going to be equal to the initial velocity times the sine of the angle. So those are some things that you can always fall back on. We'll refer to those going forward in our problems.